Today we are solving LeetCode 3129, find all possible stable binary arrays. Before we get into the actual problem, let's start with a short analogy. If you'd prefer to skip it, you can move to the next timestamp where we begin the problem directly. During a training exercise in Naruto Uzumaki creates different formations of shadow clones. But Kakashi Hatake sets a rule for the exercise. No more than a certain number of clones of the same type can appear in a row. For example, if the limit is 2, a formation like clone-clone switch is valid. But clone-clone-clone would break the rule. So Naruto builds formations step by step. At every step, he keeps track of two things: how many clones have already been used, and what the last clone type was. Sometimes a formation accidentally creates too many clones in a row. When that happens, Kakashi simply removes that illegal formation. That is exactly what our dynamic programming approach does in this problem. We build sequences step by step, track the last digit used, and remove the cases where the limit is exceeded. Now moving to the actual problem. We are given 3 values: the number of zeros, the number of ones, and a limit. Our task is to build binary arrays using exactly that many zeros and ones. However, there is a rule. No sequence of identical digits can be longer than the given limit. In other words, we cannot have more than limit consecutive zeros, and we cannot have more than limit consecutive ones. Our goal is to count how many valid binary arrays satisfy these conditions. Let's look at a simple example. Suppose we have 1 0, 2 ones, and the limit is 1. We must build arrays that use exactly 1 0 and 2 ones. But no digit can repeat more than once consecutively. If we list the possible arrays, we get 1 0 1, 1 1 0, and 0 1 1. But only 1 0 1 is valid. The other two contain 2 ones in a row, which breaks the rule. So the final answer in this example is 1. Now, when reading the question, a few signals immediately stand out. On my website, I summarize this using pattern recognition signals. First, we are counting valid sequences with a fixed number of zeros and ones. Whenever we see counting problems with a budget of elements, that usually suggests dynamic programming over how many elements have been used. Second, there is a constraint on consecutive identical elements. That means the next decision depends on the last digit we placed. So we must track the last digit in our state. Third, both the 0 count and 1 count are bounded, up to about 200. That means a 2-dimensional state table is small enough to store in memory. Fourth, the answer is taken modulo 10 to the power 9 plus 7. Large counts like this usually confirm that brute force is impossible and dynamic programming is the intended approach. And finally, instead of looping over possible run lengths, we subtract a single overflow term. This is a small prefix sum trick that keeps each DP transition constant time. So putting these signals together, the pattern here is a 3-dimensional dynamic programming state with a last digit indicator. Let's define the underlying concept. We define dpij0 as the number of stable arrays that use exactly i0s and j1s, where the last digit placed is 0. Similarly, dpij1 represents the number of stable arrays that use exactly i0s and j1s, where the last digit placed is 1. Why do we need this last digit information? Because when we extend the sequence, we need to know whether we are continuing a run or switching digits. Now let's understand the transition. To end in 0 at position I, we must append a 0 to a sequence that previously used 1 fewer 0. That previous sequence could have ended in either 0 or 1. So we add dpi-1j0 plus dpi-1j1. However, there is a special invalid case we must subtract. If we accidentally create limit plus 1 zeros in a row, that violates the stability rule. Those cases are removed by subtracting dpi minus limit minus 1j1. The same logic applies symmetrically for ones. So every state combines the normal transition with one subtraction that removes the overlimit run. This subtraction is the trick that avoids looping over run lengths. Without it, each cell might require scanning up to limit positions. With it, every DP state is computed in constant time. Now let's see this visually, using the example 0 equals 1, 1 equals 2, and limit equals 1. First, we fill the base cases. Since the limit is 1, we can only place a single 0 or a single 1 in a pure run, so dp100 equals 1, representing the array containing just 0. Similarly, dp011 equals 1, representing the array containing just 1. The empty prefix is also initialized, so the dp transitions can begin. All other cells start as 0. Now we fill the state where I equals 1 and j equals 1. First, we compute arrays that end in 0. We use the formula dp110 equals dp010 plus dp011. That becomes 0 plus 1, which equals 1. The array represented here is 1 followed by 0. Next, we compute arrays that end in 1. dp111 equals dp100 plus dp101. That becomes 1 plus 0, which equals 1. The array represented here is 0 followed by 1. So after this step, we have two valid arrays, 1, 0, and 0, 1. Next, we fill the state where I equals 1 and j equals 2. First, we try to end the array with 0. dp120 equals dp020 plus dp021. Both of those are 0, so the result is 0. There is no valid array using 1, 0, and 2 1s that ends in 0. Now we compute the state that ends in 1. dp121 equals dp110 plus dp111 minus dp100. That becomes 1 plus 1 minus 1, which equals 1. The subtraction removes the invalid array 0, 1, 1 because that creates two 1s in a row, which violates the limit. After removing that invalid case, the only remaining valid array is 1, 0, 1. Finally, we compute the answer. dp120 plus dp121 equals 0 plus 1, which gives us one valid stable array. Now that the idea is clear, let's look at how we implement it in code. We create a three-dimensional DP array where each cell stores counts for sequences ending in 0 or ending in 1. First, we initialize the base cases. For runs of zeros up to the limit, we set dpi00 to 1. For runs of 1s up to the limit, we set dp0j1 to 1. Then we iterate over every possible number of zeros and 1s used so far. For each state, we compute two transitions, one for ending with 0 and one for ending with 1. To compute the 0 ending state, we add the previous row values dpi-1j0 and dpi-1j1. Then we subtract the overflow case that would produce limit plus 1 zeros in a row. Similarly, for the 1 ending state, we add dpij-10 and dpij-11 and subtract the overflow case that would create too many 1s consecutively. Every transition is constant time, and we keep the result modulo 10 to the power 9 plus 7. At the end, we return the sum of the two states that use all zeros and all 1s, ending in 0 or ending in 1. Finally, let's talk about complexity. The dynamic programming table has roughly 0 multiplied by 1 states. Each state is computed in constant time thanks to the subtraction trick that removes the overflow case. So the time complexity is O of 0 multiplied by 1. The space complexity is also O of 0 multiplied by 1 since we store two DP tables of size 0 plus 1 by 1 plus 1. With the given constraints, this is only around 80 kilobytes of memory, and that's the complete idea behind this problem. Thanks for watching. If this helped, consider liking, commenting, subscribing, and sharing. For more problems explained like this, check out the playlist linked in the description.